Hello there, and welcome to the first episode of Complex Conversations. I am your host, Isaac Bates, and today I'm joined with Matilda Huggett and Louis Nunn. We will be discussing the basic mathematical concepts surrounding the Mandelbrot set. So let's start. So what is a complex number, Matilda?
So a complex number is a number that is made up of a real and an imaginary part. Imaginary numbers are represented as I and are root -1. And I squared is -1. A complex number is expressed as z equals a plus bi.
Alright then, so a complex number is basically a two-dimensional number. But how can we perform normal mathematical operations like addition and multiplication on these complex numbers?
Well, Isaac, to add complex numbers together, you simply add the real parts together. So here it would be 5 plus 12 for 17. And you add the coefficients of I. So 2 plus 9 is 11, giving you 17 plus 11i. And to multiply it, you simply do it how you would expanding brackets normally. So we do 5 times 12 for 60. Add 5 times 8i for 40i. 2i times 12, so 24i. And then 2i times 8i, which gives us 16i squared. And as Matilda said earlier, I squared equals -1. So this equals subtract 16. And then we just simplify this to get 44 plus 64i.
Thank you. So, how can we graphically represent a complex number?
So we represent complex numbers on our diagrams, right? So the x, y, so the diagram is just a normal x and y axis. However, the x-axis is represented with real numbers and the y-axis is the imaginary. Let's take a complex number, 3 plus 2i. To do this, we put the 3 on the real axis and the 2 on the imaginary axis. And this would be how we represent a complex number on an Argand diagram.
So Argand diagrams are basically just number lines for complex numbers. But is there any more properties of complex numbers we should understand?
Well, Isaac, the modulus of a complex number is essentially the length of the line on the Argand diagram. So you just use Pythagoras' theorem to find it. So you know this is 3, that's 2. So it's 3 squared plus 2 squared all square rooted, which is 3 squared plus 2 squared, which is the square root of 13.
Great. That's all on complex numbers for now. We'll be back with this in a bit. So next up, to understand the Mandelbrot set, we need to understand about sequences. Matilda, what is a recursive relationship?
So a recursive sequence is where the answer to the previous term is substituted back into the sequence to get the next term. So let's take this and we'll take a equals n plus 1 equals an plus 4. a1 equals 1. We take that, put it back into this to get 1 plus 4 equals 5 as a2 resulting in 5.
Well, do these recursive sequences have any properties worth mentioning?
Well, these recursive sequences can either diverge or converge. Diverge means that they just keep increasing and increasing towards infinity, whereas converging means that they just get closer to a specific point or fluctuate between 2 points. So they converge to a point or are bounded to a certain point.
Thank you very much. Finally, what is a fractal?
A fractal is a geometric shape which displays self-similarity at different scales. The fractal replicates itself as you zoom in. A true fractal will never get simpler or smoother.
How does the Mandelbrot set tie into all of this?
Well, the Mandelbrot set is a fractal which is generated by a computer by calculating an equation over and over and over again.
Any interesting real-life fractals?
A good example of a real-life fractal is a cauliflower. Let's take a cauliflower. We cut a floret off. It's almost like a secondary, smaller cauliflower. Then you continue cutting it repeatedly till you get smaller and smaller, similar cauliflowers, till you can no longer do it because the cauliflower is too small. This is a good example of a real-life fractal.
Thank you, Matilda. I'm never looking at a cauliflower the same again. Thank you for listening to the first episode of Complex Conversations. Next time, we'll be talking about the less simple to understand concepts around the Mandelbrot sets. See you then. Thank you for listening.